Hello. So I will talk about this poster about a combination of Landau-de Gennes model, which is basic for liquid crystals, with Skyrme model, which is popular for modeling of particles. So the main reason is to recreate first electromagnetism, but also the Cornell QCD potential, QED. So okay, so let's start with liquid crystals. So, like here, there are many articles which are recreating particles as topological defects in liquid crystals like this, and then looking for them in various distances at such two topological defects. Here is some time versus distance plot, and you can see they observe long-range interactions. Yeah, so they get quantized charges as topological, and the dynamics agree with the Coulomb-like dynamics. So there is this analogy between electromagnetism and hydrodynamics, like here. The main difference is that here is speed of light, here is speed of sound. It's for a superfluid without viscosity. However, it misses charges. And in liquid crystals, they can get these charges as topological defects, like here. Okay, but it's not exactly Coulomb, so we'd like to make it exactly Coulomb interaction with electromagnetism. So we would need the Lorentz invariant Lagrangian to get both. Okay, so going to electromagnetism, so here is the standard Gauss law, which has this problem that it returns charge being a real number. However, in nature, this charge should be integer number. We have the charge quantization. So there is this topological version of Gauss law. It's called Gauss-Bonnet theorem, which uses curvature here. So if defining this curvature as our electric field, our Gauss law would return integer charge, topological. So here is such. Here we can use the field of unitary vectors n, then define its connection as local rotation as gamma, which corresponds to the A field. Then the curvature as like here as the cross product. So now we would like to interpret this curvature as F tensor dual, more precisely, to get electric monopoles, not magnetic as often. And for this this F tensor as curvature, we use standard Lagrangian of electromagnetism. This way we will get electromagnetism with built-in charge quantization as topological. So this is Manfred-Faber's approach. Okay, so here is calculation that indeed we get a Coulomb potential as effective. So we take two topological charges in various distances. Here are the same, here are the opposite, and calculate the energy of such system by integrating the Hamiltonian as sum of squared curvature as previously. So here is the Hamiltonian. We integrate it over the field, and this way we get the dots here. So then then there is fitted also 1 over R potential, and we can see that it's nearly perfectly agrees. Yes, so effectively these two topological defects with this kind of Lorentz invariant Hamiltonian indeed get effective Coulomb potential. So, however, there are these problems in the center of charge. So it will have infinite energy. Charge has infinite energy in the center. So also here we have this problem. If you have topological charge like here, there is a problem in the center. There would be some discontinuity which would lead to infinite energy. So here we need to use Higgs-like potential. So for example, for Higgs potential, it prefers unitary vectors. However, it allows them to deform to, let's say, zero vectors to avoid singularity. Yeah, so asymptotically we have that electric charge as topological. However, near the center of the particle, something happens to avoid the singularity, deforming this shape. And then sound as this deformation, so Manfred-Faber has calculated with him, this Coulomb interaction. So you can see that the red dot versus the Coulomb, the blue line. So you can see that the Coulomb becomes slightly stronger than usually for very low distances. This is femtometer distance. So this way we get increase of alpha running coupling constant of Coulomb interaction in very low distance, that means very high energy, what is well known as the running coupling effect. Yeah, so that in very high energy, the alpha controlling Coulomb interaction is increased, like here. And Manfred has tested that indeed they got this kind of effect with by just regularization of singularity. Yeah, so imagining electron as a perfect point, there is this problem that integration energy of its field from 0, we get infinite energy. If you integrate from 1,4 femtometers, we get energy like mass of electron. So we need some deformation in this like 2 femtometer distance, and this deformation indeed leads to running coupling effect non-experimentally. So let's take a look at some arguments for the size of electron. So the standard one is based on G factor. It was started by Delmet, who has drawn this plot. You have a triton as made of 3 quarks, triton as made of nucleons, proton as made of 3 quarks, and finally hypothesis that electron is made of some 3 partons. So from one side, we don't assume here any partons. We just deform the singularity. From the other, if you take a look, so just drawing a line, he would get negative radius. So here is radius on the horizontal axis, and on the vertical is g minus 2. So what he did, he extrapolated from 2 points with parabola. So we cannot do it. So it is not a proper argument. So let's take a look at more serious arguments. So the electrons positrons cross section. So here is some for very high energy. This is Gauss, so extremely high energy. But we are interested in the size of resting electron. So we should just take this line here and extrapolate it to 2 times 511 keV mass of resting electron plus positron. Doing so, we get approximately 100 millibarns, which corresponds to approximately 2 femtometers. This is exactly in agreement with this requirement, range of deformations not to exceed mass of electron with energy of its relativity alone. Yeah, so there are many arguments that electron is not a perfect point charge, but it is the regularized not to exceed mass of the electron, so we have finite energy. Doing so, indeed, we get this kind of behavior and also running coupling, which is in agreement. So electron has also more properties. Yeah, so this is not only electric charge, but it also has magnetic dipole moment. It has also angular momentum. This is very real angular momentum. So not of point. Imagining as a point rotates, it makes no sense. But we live in field theorem, so a field should rotate. So it has angular momentum in another theorem. Also, electron has the clock, the Broglie clock Bewegung, which is required by this phase evolution, quantum phase evolution, using mc square as the energy. Yeah, so literally the mass of electron propels its clock. So this the big question: how it's happening? I have some approach I mentioned further. But generally, we need some clock, some angular momentum, magnetic dipole moment. So how to get it? So here is my approach, that we have the hedgehog as topological charge. Yeah, so the long axis forms a hedgehog. So asymptotically, we get just on topological charge. However, it also recognizes twist of this field. Yes, and this field can rotate. So the evolution should be indeed like here with the quantum phase. So this twist corresponds to the quantum phase. So this way we get the clock, but also angular momentum, rotation of the field, not of the point. But it also leads to the magnetic field, magnetic dipole moment. Okay, so let's finally think about this dynamics of vacuum. Yeah, so we have started with unitary vectors, and they get to electromagnetism. Then we add a twist as quantum phase. So it is indeed in QED Lagrangian we have both this high energy electromagnetism, but also low energy H bar C contribution of quantum phase evolution. Yeah, so they are both. So also this twist is there, but with much lower contributions. And indeed, if you have this kind of elongated molecule like in liquid crystals, and these tilts are high energy and twists are low energy, we can get the coefficients, that the contributions are like in QED. Yes, that's the goal, to unify both the electromagnetism and quantum mechanics within this SO3 rotation in the space. The tilts, high energy tilts for electromagnetism and twists for quantum mechanics. Moreover, so we live in 4 dimensions, so we should not just use SO3, but SO13, Lorentz group, so add boosts. So we have also boosts here, yes, that this local boost direction, I don't know if tilde. So it turns out that it leads to the second set of Maxwell equations, as it is called gravity-electromagnetic approximation of general relativity, which was used, for example, for the gravity probe calculations. So we just have the second set of Maxwell equations. Yeah, so if you start with Coulomb, it's not Lorentz invariant. We need to add magnetism for Lorentz invariance, and the same you can do with Newton to extend it with to Lorentz invariant with the magnetic analogy of magnetism. Additionally, there is also interaction between electromagnetism and quantum mechanics, the boosts and tilts, rotations and boosts. So this interaction slows down electromagnetic propagation in high gravitational fields. Yeah, so having such slowing down of electromagnetic propagation, we get both the gravitational time dilation, because all chemistry, for example, is based on electromagnetic propagation, and also we get the light bending because because of the Fermat principle. Yeah, so we can also get unification of all these 3 long-range interactions by just SO13 field. So from tilts we get electromagnetism, from twists we get quantum mechanics, and from boosts, which are very unlikely. So the cost is very high to make a boost, which leads to kind of local space curvature. So space-time can be flat here. And so from these boost dynamics, you can set second set of Maxwell equations, which agree with the gravity electromagnetism. Okay, so let's take a look finally at the candidate of the Lagrangian. So we have this electromagnetic-like part, F mini, but with using F as curvature of some deeper field, because we would like to have the Gauss law count topological charge of of this deeper field, because the nature has a charge quantization. So this F is some curvature of this deeper field, which can be described this way. And we need this Higgs-like potential, which prefers a shape of our molecule. Yeah, so this set of eigenvalues. So our field is this M, which can be decomposed locally as this diagonal and applied first rotation, and then as also boosts. So, and this D prefers some set of eigenvalues. So there is, let's say, 1 for the electromagnetism, but also this tiny delta for these very low contributions of quantum mechanics in the QED Lagrangian, for example, and then also there's G much larger to describe the strength of contribution of local boosts for gravity. So here we get some 2-level standard. So we say that electromagnetic field F tensor are not fundamental because there is deeper A field, for example, in Aharonov-Bohm effect. And here we say that we need even deeper field because of the charge quantization. Yes, because the original electromagnetic A fields do not have charge quantization. We need to introduce some deeper field, define that A is connection of this deeper field, F, EB are curvature of this deeper field. This way, the Gauss law counts this topological charge of the deeper field, getting charge quantization. And here is this F tensor, if you write it in the curvatures. So here is R1 is this basic curvature for electromagnetism, for the Gauss law with charge quantization as topological. We have also this smaller contribution from the interaction with tilt in one direction and twist in the second. So we get this quantum mechanics here. And finally, there is curvature for boosts. Yeah, so which leads to second set of Maxwell equation for gravity. And there are also these terms which have negative contribution in Hamiltonian. So if we use standard Lagrangian for electromagnetism with two indexes, F mini, F mini, then going to Hamiltonian, we get only positive energy contributions. However, if you use four indexes, then going to Hamiltonian, there are also negative contributions. So we get also the negative curvature square contributions. And they seem exactly what is needed both for the clock of the particle, that resting electron, resting neutrino already oscillate, have angular momentum. So here we get this gamma one. Gamma one is this twist. Yeah. So this is energy preference because this is negative term in energy density. This preference of the time derivative in the presence of some local boosts. So this term should give both the preference for the clock neutrino oscillations and for gravitational mass. Yeah, so that's the big question, why the particles also have gravitational mass, and I think also because of this term. Okay, so going further, beside the point-like topological defects, we also need vortices, topological vortices. And in particle physics, they are also well known as quark strings, that we have quark, anti-quark, and between them there is this one-dimensional structure, which also requires this topological vortex. So the big question is how to add quarks as fractional charges to this topological vortex, and we can do it. So let's think about it. So here is this topological vortex, and now we perform this rotation, inward outward field rotation of this vortex, like here. So if you would rotate by pi, then we would get a hedgehog. So we would get topological charge, elementary charge. However, if you do 1/3 of pi, then we get fractional charge. Yeah, so we get fractional charge. Then we can have to reverse it. So we get quark anti-quark kind of. But however, there is a problem. If you do just by third, there is the field here has some conflict. There is some problem here in the center, especially. So this problem means that there is requires some energy, and asymptotically it should be linear energy per length, yes, because it should have nearly constant shape. So we this way we get this well-known this Coulomb Cornell QCD potential, like that. First we have Coulomb interaction between charge charge quarks, and asymptotically is linear. So literally from bending the topological charge quantization. Yeah, so we have charge quantization. Usually particles are only have integer charges. However, it is believed to be bent in quarks. But this is at cost. So this is at cost, which grows linearly with the distance between the two quarks. Yeah, so there is some conflict, and asymptotically needs linear energy. So our Gauss law, the topological Gauss law, has integer unless it cuts a singularity. Yeah, so the Gauss law cannot count singularity. So if the Gauss law counts this topological vortex, then it can be fractional because it cuts singularity. Okay, so finally, we can think about, so if you have this topological, if you have these quark strings as topological vortex, for example, they are considered, widely considered inside the nucleons. However, if they are inside nucleons, why not also between nucleons? So maybe they are also important for binding of nuclei. And I think that the best argument for that are the halonuclei. So halonuclei, like lithium-11, have like 2 neutrons in very large distance, like 5 femtometers. So this is a few times larger than of nuclear force. Yeah. So it brings question why they are bound for milliseconds, a very long time, in many times larger distance than nuclear force. Additionally, turns out it needs 3 body forces. So I think reminding that there is this quark string, like one-dimensional structure. So if it binds, let's say, go here and go here, like here. So maybe the topological vortex goes through both. Then it could stabilize them for milliseconds to explain this binding. And also, if we would like some effective descriptions of such binding by one-dimensional structure, we would need 3 body forces. So I think everything here agrees that we should remind that there are this one-dimensional structure, and that they should also go outside of nucleons, also help with binding of nuclei. So maybe instead of these grapes for nuclei, we should think about them later as knots of this topological vortex as quark strings. So finally, There is string hadronization. So in LHC especially, they believe that in these collisions there is created these quark strings again, like here, and now these quark strings decay into particles. So if in non-perturbative picture the quark strings correspond to topological vortex, then we just need to find the correspondence between what topological vortex can decay into and what they observe in LHC collisions. Yes, so for example, these quark strings, topological vortices can form a closed loop. Yeah, so we need this kind of structure. So they should be created, for example, in LHC collisions, and they should correspond to some particles. So which particles? So let's think about it. So they are very light and stable. They can be in one of three types because we have three dimensions. And so they can evolve through each other and oscillate between them by just field rotations. So they seem very similar as the neutrinos. Yeah, so I think this is natural candidate for a neutrino. For if there is some additional twist, like Mobius string, there is suggestion that it might be strangeness. But first of all, if we believe that these topological vortices are crucial in nuclei, then baryons should be also the simplest knots. Yeah. So so let's think about the baryons now. So here is a simplest knot of such topological vortices. So we have one vortex inside and the second around. If you look at cross section, so we can see that the vortex around deforms the field of the internal vortex, and it deforms it exactly toward the hedgehog. And hedgehog for us is topological as electric charge. Yeah, so proton can just enclose this hedgehog, while neutron has to compensate it. So yeah, so neutron also has this preference, but then it has to compensate it. So this way we just explained why neutron is heavier, because this compensation is costly. Yes, these are some additional high energy structures. Also, it is known that a neutron has positive core, negative shell. So here is some distribution from Wilson. For proton is only positive. For neutron is positive core, negative shell. Therefore, deuteron. So it is known that it has electric quadrupole moment. So it should be plus minus plus, and we exactly to get it. So both baryons require charge, and now they share one charge to satisfy this preference for charge, getting the binding. Yeah, so you get plus minus plus, you get quadrupole moment as required. So also we get this beta decay in agreement between the neutron and proton, producing this kind of neutrino-like structure. So releasing part of the energy difference into these quark strings. Also, if you had the hedgehog, you can perform the hedgehog in one of three axes, so getting three types of objects having the same electric as topological charge, but different realization, different regularization, so different mass. So like three leptons. And also here are the three quarks candidate. Yes, so we have this vortex and this binding or not because of this external vortex. So this external vortex around can enforce it, and for the quark, for this minus one third, they are like in neutron for compensation. Yeah, so we can explain why we have three families of quarks, leptons, neutrino, because we live in three dimensions. So the field has three axes and can get for charge, it can be hedgehog of one of the three axes. For topological vortices, it can be vortex around one of three axes. So I think it's natural explanation that we have three families because we live in three dimensions. Okay, thank you for interaction. So